Yeah, I know.
Oh, yeah.
That's good.
Yeah, it's like, yeah. Yeah, we did it. Okay, yeah.
Yeah, we did like a. But it was really
Where did you go?
It wasn't like a touristy place. It was like this has some good.
Oh, okay. Yeah.
But it wasn't too touristy. Yeah, it'll be like big, but it's pretty nice. Yeah, it was nice. I don't think so. Yeah, it was good. Yeah. I'm with my roommate and yeah. Yeah.
Yeah, it's not like
It gets hard.
I know. Or I.
Yeah. Oh, with it.
Yeah.
Yeah. Yeah. I know. You know. I just don't. Yeah. There are also good Vegas. Yeah. Right.
Let's get those spring break cobwebs. Ahead. Everybody had a good break. Into the final push. Okay, so plan today, and I want to go back and revisit the thermodiagram. There's a lot of information coming at you in drawing those pretty pictures. So let me do some review on that. Then finish off the little bit that we didn't cover, the convective available potential. That should set you up for hopefully success in doing the take-home exercise. And then we will get to talk about thunderstorms. That's the plan today. And it seems like all technology is still on spring break. I can't get the clicker to work, and I got a second one, and I do have a third one, but none of it works. So we'll just have to do it the old-fashioned way on the keyboard. All right, so as a quick recap then, we got to this point, and again, I know it's such a simple data set, right? Just to plot 6 or 7 or 8 vertical temperature soundings and dew point soundings, but it is a complicated diagram, right? There's lots of things going on this diagram. So let me just recap where we are. So if you remember, we plotted the vertical sounding, the red circles are the temperature and the blue X's were the dew points, right? So you're looking at what is the atmospheric moisture content the actual air temperature of the environment at different altitudes. From that, you can glean a number of things, and really most of this is focused on determining what layers are stable and if your parcel will be stable. Because ultimately, that's going to lead us to the second part this morning, which is thunderstorms, right? At what point, under what conditions, what do you need to do in the atmosphere to get that free, rapid uplift? Because that's what we want if we want severe storms to develop. We've got to have rapid uplift, rapid cooling, and all the things we've already talked about. So we plotted the dew point and the red circles, which is the atmospheric sounding, the temperature, and then we said, okay, let's lift that parcel from the surface, right? And we lift it from the surface at the dry adiabatic lapse rate. You know it's dry because the dew point and the temperature are so far apart, right? Remember, one of the important parts here is the mixing ratio lines, these dashed lines that go from top left to bottom right, right? How many grams per kilogram of actual moisture is in that parcel? At the surface, remember the mixing ratio line that passed through here, it's that dashed line there. And there's lots of dashed lines on here, but it's about 21 grams per kilogram. And we said that if that air parcel was saturated at the surface, then the mixing ratio line would be through here, and you follow that up to something like 50 or 52 grams. So we know that that parcel is unsaturated, right? The dew point and the air temperature lie far apart. Obviously, if the red dot and the X are on top of one another, then you'd have 100% saturated air at the surface. Okay, cool. So we then lift that parcel theoretically along the dry adiabatic lapse rate, and you lift the X, the dew point, along the mixing ratio line. The actual amount of moisture in that air parcel at the surface in all of this work is not going to change. Okay, so there's no exchange of moisture from outside to within that parcel. We're going to keep that parcel isolated. In other words, we're going to have 21 grams per kilogram of moisture in that parcel. So the blue line and the red line meet. Okay, at that level, remember, we're at the lifting condensation rate, right? It's the level to which the air needs to be lifted in order for saturation to occur. So at that point, the air temperature, remember, which is the red dot and following the red line at the dry rate, matches the dew point temperature, the relative humidity is 100%, you're at the lifting condensation level. That's all good, okay? Of course, that wouldn't happen in this example. Why? Because as you lift that parcel of air along the dry rate, okay, it gets to the point where it intersects the ambient environmental lapse rate, and it would stop rising there, right? Because that's where that parcel becomes neutral, okay? Its temperature is the same as the surrounding environment. Everybody good there on that? Okay.
Will you repeat that, please?
Which part?
The part you just said about the cat.
Yeah, so we're lifting that parcel conceptually, right, from the surface, and we're going to lift it to where it meets the dew point. The dew point comes up, that's the lifting condensation rate. The problem here is that it's not going to pass through this ambient environment, right? So here, as that parcel lifts, it's always warmer than the surrounding environment. It's warmer than the surrounding environment. It's unstable. It's buoyant. Everything's good until it meets that air parcel there. Then it's neutral and it stops right there. So under this condition, yeah, you plotted the lifting condensation level, but the parcel is not going to reach that lifting condensation level. It intersects, quote unquote, the environmental lapse rate. Okay? So it'll stop right there. But if you somehow could get that parcel to its lifting condensation level, right, then it would continue to rise, not on its own accord here, because it would not get to this point. But if it would continue to rise, and it would cool at the saturated adiabatic lapse rate. Okay, and as it rises and cools at the saturated adiabatic lapse rate, it's when it re-intersects the environment that it becomes at the level of free convection. Right? In other words, if you were to take your hands off that parcel at that point, it would actually just shoot up along that green dashed curve, because now its temperature is always warmer than the ambient environment. So the problem in this example is you've got this little orange area here, which is the convective inhibition, right? That's the lid that's keeping everything under wraps until you can break through it. Now, if it, let me get a red one. So yeah, that's a red one. If the ambient environment had done this, it would have been much more simple. So if that was that red dot there, okay, and the next red dot was here, right? In other words, if the ambient environment had done that, See that? If that was your data point, then what does that mean? What would happen? Well, that parcel would have come along the dry adiabatic lapse rate, right? It would never have intersected the ambient environment. It would have reached its dew point. This lifting condensation level would have coincided with the level of free convection. It would have then just continued to rise along the saturated adiabatic lapse rate. It would always be lying to the right of the environment. It would always be unstable. You would be off to the races, and you would have unrestricted uplift or convection going on in the atmosphere at that point. Does that make sense? Right? So if the environmental lapse rate is steep, in other words, if temperature is changing quickly with light, then we wouldn't have had any convective inhibition whatsoever. We would have had free convection. Right? Does that make sense? Okay. So that's I think where we left off, and then the limit of convection is the top. The final thing I wanted to talk about, I'm sorry, I'm going to have to come back to the keyboard every time to do this, is then this, okay, how do we determine how much convective potential there is in the atmosphere? Okay, you can have a really calm morning, and there could be a very high convective potential, depending on whether you have an inversion and depending on just what sort of lid you have, right? So we call that CAPE, convective available potential energy. And the CAPE is simply the shaded area between the actual environmental sounding and the saturated adiabatic lapse rate. Because remember, the air parcel, once we get it to its level of free convection, it's going to rise and cool at the saturated adiabatic lapse rate. Okay, that's great. How quickly will it rise, and what is the potential for convection and storms, and by extension, I can't speak this morning, extension is severe thunderstorms, right? So the convective available potential energy is just simply the area inside this shaded part here between the environmental lapse rate and the saturated adiabatic lapse rate. Does that make sense to everybody? So how do we determine whether there's a high level of potential or a low level of potential? So it turns out all you simply have to do, right, is count the number of these little boxes. So these little boxes, these sort of parallelograms here, okay, these boxes are the boxes that are defined by the isotherm. So these are the 5°C lines and the 1 kilometer height. Now I know there's a million different dashed lines going on here at the moment, right? But the convective available potential energy boxes are these ones here, right? The height lines going down to the right, those ones there, and the temperature lines going down to the bottom. Okay, there are those little boxes, and you just simply count up the number of those boxes. Okay, so the convective available potential energy. There's the little table on the right. Okay, there's a couple of ways to look at it. We're just going to look at it for this left part of the table. Right? You count up the number of boxes, and if the number of boxes are less than 26 and greater than 0, so somewhere between 0 and 26 boxes, then you've got, or not boxes, but the degrees Celsius kilometers, then you've got very weak or very limited convection. And the more boxes, the greater the convective available potential energy. So just take a look at how this works. Okay, you count the number of boxes, and each of those boxes are 5°C wide by 1 kilometer high, right? Because you've got those kilometer height lines and the degree Celsius boxes. So each box is 5°C by 1 kilometer, right? So the area in each box is just simply 5°C kilometers. Cool, so we count up the number of boxes, right? So each one of these little blobs I've put on here is a box. Okay, so you count up the number of boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 full boxes. And then you start estimating whether you have a quarter of a box or half a box or whatever the case may be. So here's one, for example, right here, okay, which isn't the full box. Okay, that's kind of 3/4 of a box, right? And then you may have one that's another 3/4 of a box there, and you've got a little edge there. And you just count them up until you estimate, well, 1 3/4 and 1/4 makes a box, so that's another one. And it's a reasonably rough estimate, but at the end of the day, you count up the number of those boxes, okay? And that'll give you the convective available potential energy. So in other words, in this example here, let's say you counted up 23.5 boxes, right? So that's 23.5 boxes. and you just multiply that by 5 degrees Celsius kilometers. So 23.5 boxes multiplied by 5 degrees Celsius kilometers gives you this number here, 117.5. And you just look over here, how much Cape do we have? Well, the Cape is greater than 92, yeah, it's 117. We've got a huge amount of convective available potential energy. If the line is this, right, if you had, try and keep the colors the same, okay? If this was your saturated adiabatic lapse rate, and that was all you had in terms of the Cape, right, and you ended up having, say, 2 boxes. 2 boxes times 10 is 20, right? Your Cape would be somewhere in here, between 0 and 26, weak convection, maybe you'll get some cumulus clouds, 0 chance of severe thunderstorm, right? So the bigger that area between the saturated adiabatic lapse rate and the environment, that gives you a higher convective potential energy. It's a lot greater likelihood of severe storms. So that's where we need to end the thermodiagram. That's the last bit that you'll do, everybody, on the take-home exercise. So let me just stop there. See what questions you have. That was quite a slog to go through that. Yeah.
It's kind of a logistics question.
Yeah.
Do we just get another, is this what we do the thermodiagram?
Yeah, you do that. You do that on. But, yeah. So I can bring some more to you on Thursday. But it's also online, so you can download it. But I'll bring a bunch. Name one or two. It's really not a huge exercise. It'll just take time for you to plot it, right? So try and get that done. Great opportunity to get your grade going.
You said, to record this.
Record what?
The presentation.
Yeah. You have that. And I know I'm not supposed, what I do is I record every lecture, so I see the Zoom up there, and I give that link to people who have the university excuse. But I'll make the thermodiagram one of it, because that's just because I know you want to listen to it 3 or 4 times. Any other questions on that? All right, cool. Okay, so let me just exit that and just give me a minute, please. I need to reshare the screen on another PowerPoint, so let's do that. All righty. Okay, well, that's a fail. Okay, so we had a little visit from some thunderstorms last night. So this is pretty relevant. This is actually a very active time of year for thunderstorm development, right? Spring storms in Texas. It's not that we only get thunderstorms here in spring, we get them throughout the year, depending on what the trigger mechanism is for those storms. And that's a term we're going to come back and look at a little bit this morning. So let me just write that up as a frame of reference. We're going to have to talk about triggers. Because you may have a completely stable atmosphere, and that stable atmosphere might have a high convective available potential energy. How would that happen? Right? Well, it would happen if you've got a strong inversion, keeping a lid on everything that's going on down below. Right? So you can have a stable atmosphere, a quiet morning, and you can have a very strong thunderstorm potential. And conversely, you can have a fairly active lower atmosphere. It can be warm, humid. You may see lots of clouds, right? It may be rainy, but you may have 0 potential for convection in terms of severe thunderstorms, because a lot of it comes down to this, right? A lot of it comes down to, do you have the correct trigger mechanism that can sort of fire the starting pistol to get things up and running, if you like, okay? So let's talk about thunderstorms. And I won't use the term severe yet, because that has some very specific meaning in meteorology. So we want to talk a little bit about thunderstorms at the outset, and then I'll come back and build in severe storms when we actually get to that section, not this morning, but that will be with tornadoes and so on. So first off, let me just get some clarity here. So here's I have a weather app. I've got about 10 on my phone. And you'll see a daily forecast. And I just wanted to get this term out of the way where you see a forecast, it's the highs and lows. And the weather app will say there's a 90% chance of rainfall. Apparently it will do 0.49 inches, and there's a 90% chance of that. What does that actually mean? Actually, some of these apps really make me chuckle, because not only will they give you 7 days out a detailed trace of what the rainfall is going to do, but they'll have those percentages, like there's a 63% chance or 41%. That's guesswork, right? That's just total thumb sucking that's going on. It's just TV stations or apps want to make themselves sound more scientific or accurate or precise than they actually are, right? So looking at an exact rainfall trace 2 weeks out or 10 days out or 5 days out is quite a fair amount of guesswork. And we'll talk about that when we get to weather forecasting. But at around a percentage, what does 90% mean? Okay, it does not mean that 90% of the area is going to get rainfall. All right, it's a probability. It's just a statistical probability. Okay, and it's the probability that we'll get measurable liquid. In other words, anything above 0.01 inches. And that's going to occur at any specific location in the forecast area, right? So if your forecast area is the DFW Metroplex, and it's calling for a 50% chance of rain tonight, it doesn't mean to say that Arlington's likely to get it and downtown Fort Worth is not. It's a broad statistical probability, which means the 50% chance of rain tonight means that there's a 5 in 10 chance at any point in the region covered by the forecast will receive measurable precipitation. Okay, that's all it means, right? 70% chance means there's a 7 in 10 chance, the roll of the dice. Okay? And obviously, as you start getting a higher probability, they get more comfortable with that forecast. And if you've got a frontal system coming through, and you know that front's going to come through, and all the models are predicting the front will come through, and you've got high humidities, then you're probably getting up into the 95 to 100%. But they won't issue 100% probability unless they are absolutely certain that something is going to come through. So just bear that in mind, right? It's not a spatial coverage. It's just simply a probabilistic statement. The other term you'll see with thunderstorms is something like this, right? The talking head on TV will say, well, we've got isolated storms, scattered storms. These do have some broad, again, statistical meaning. So if we're talking about scattered storms, it means that 30 to 50% of the area is likely to be affected by those storms. So just again, be aware of the difference in those two terminologies. I will say that one of the most difficult things in weather forecasting are convective thunderstorms, right? Because sometimes you can get it so right, and sometimes you can be completely off, because convection depends on differential heating largely. Unless you bring a front in, you've got a strong front, and you know that storms are all going to be lifted up along that front. If you're just dealing with a hot summer's afternoon, it's notoriously difficult to pinpoint exactly where convection will happen. And again, we'll look at that, everyone, when we come to the weather models a little later on, right? Some models are better than others when it comes to convection. But anyway, that's just some terminology to get out of the way. Okay. So just as a recap here, remember the key thing in all of this, right? The most important thing when it comes to forecasting storms is to determine that LFC, right? That level of free convection, and the likelihood that an air parcel is going to reach that level of free convection, right? So on the left here, this is from the book. Here's a simple example. Let's say the red, that looks like the morning sounding. Okay, so you send up the weather balloon, and the red line gives you the environmental lapse rate. And then we say, okay, here's our parcel at the surface. We're going to lift it at the dry adiabatic lapse rate. We're going to reach its lifting condensation. It'll now cool at the saturated adiabatic lapse rate, and it'll intersect the environment there. That's the level of free convection, right? So above the level of free convection, of course, the parcel is positively buoyant, meaning that if you can get it there, you can take your hands off it. Then you're off to the races, right? Then you will have unrestricted or unaided up. Okay, that atmosphere is going to be conducive to upward motion. So that's great, and you have to have that for any kind of storm development. You've got to get your air parcels above the level of free convection, right? Again, we're going to come back to that term triggers, and I'll show you what those triggers are as we go through this morning. one of the easiest ways to do that is afternoon heating, right? So if you heat the ground, and I talked a little bit about this last time, I know it's been a week or two, but your morning sounding could look like that. Okay, so you may actually have an inversion here at the surface, which is extremely stable. But if you go through afternoon heating, the surface temperature might look like that. Okay, and you may be able to, that's the easiest way to get air parcels to their LFC, right? It's just intense summertime heating. It destabilizes the atmosphere. You may hear that on TV or forecasting. Afternoon heating will destabilize the atmosphere. How does it do that? Because it changes the dynamic between the temperature sounding and the dry adiabatic lab stress, right? So just bear that in mind. That's one of the triggers we will talk about. Okay. However, having said that, okay, we cannot just default and say, well, the only way we can get thunderstorms is to heat the ground, because heating the ground will destabilize the surface. Warmth at the surface does not always mean that the atmosphere will blossom with thunderstorms. You may have a warm, humid summer afternoon, right? And the dew points may be 75 degrees Fahrenheit, with lots of moisture coming in from the Gulf of Mexico, outside temperatures may be 95, and you may just see a whole bunch of puffy popcorn-like clouds in the sky. Okay, why don't you get thunderstorms developing? Because there's something keeping a lid on the atmosphere, and that atmosphere cannot get to its level of free convection. So warmth at the surface doesn't always mean the atmosphere will develop thunderstorms. It certainly helps, but it's not guaranteed, okay? And of course, thunderstorms can occur even when the air near the ground isn't very cold, right? Last night was a good example, right? I don't know what the temperatures were out last night when the storm came through, what, 55, something like that, maybe. So fairly cool, and yet we've got lightning and thunder, and we've got storms in the area. Why? Because we've got the right trigger mechanism. Okay? It just happened to be a cold. So that's just a caveat, okay? All right, so what are these lifting mechanisms then? Let's talk a little bit about what these triggers are, okay? Having said all that, having looked at the importance of the vertical sounding, the level of free convection, what are the lifting mechanisms? Well, the weakest lifting mechanism is what we call non-frontal convergence, okay? So that is just air coming together, no front involved. You may have a warming area. So let's say, do a very simple example, but let's say we've got a very large parking lot, and that parking lot is heating up during the day. Okay, that causes the air to rise. It lowers the pressure, and you've got air coming in towards the center of the low pressure. So summertime heating causes lower pressure at the surface, and that causes convergence, right? But it's not especially vigorous. It will get air going up, okay, and we see that. For example, I think I used that example when we talked about stability. You've got an island sitting in the middle of the ocean. And what do you tend to happen? You get clouds developing over that island, generally speaking, in the mid-afternoon because of the differential heating, right? That island heats up, the air rises, it cools, it gets to its dew point, and the air gets sucked in towards that. And so you have non-frontal convergence, but that's the weakest, okay, form of trigger, right? There's another lifting mechanism, tropical convergence, tropical cyclone convergence. So we're going to talk about this as a whole separate thing. Okay, this is part of tropical weather. We'll get to this next week. Hurricanes. Okay, what are hurricanes? Hurricanes are just simply really well organized thunderstorms. That's all they are, right? And so, but there's a whole series of things that have to happen in order for this to occur. So this is a spiral rain band. Again, we're going to look at the dynamics of that. And what is a spiral rain band? It's just a well organized line of thunderstorms. Okay, so this is convergence. It's air coming together and rising over tropical waters. So that's the trigger, okay, tropical convergence. So that's another one, okay. Here's a big one, right? This is exactly what happened last night. Frontal convergence, okay. You may have, and I've said this several times, so I apologize for beating a dead horse, but it's important. You may have a lower atmosphere that is stable, right? The air doesn't want to rise. But as soon as you bring a cold front in there, that becomes the trigger. Right? Because the air is cold and dense, and if you force cold air into a region, any kind of warm air in front of that is forced up the cold front. Okay, And as we will see, we still have to get there a little later on. But if this is the surface here, the cold front, okay, is a big wedge of cold air. So on a weather map, that is what a cold front would look like at the surface, okay? But a cold front is literally like a big wedge of cheese, okay? It's a big dome of cold air. And when that cold air gets forced into warm air, that warm air can only do one thing. If you've got any warm air here, it will rise up along that frontal boundary, okay? And a cold front, that frontal boundary is actually pretty steep. So that warm air has a very short horizontal distance to move before it starts going vertically pretty quick, right? So the distinguishing feature with frontal convergence is our thunderstorms that develop along a line. And I'll give you a couple of specific terms in just a little bit about how we look at that, right? But fronts are one of the key lifting mechanisms for thunderstorm development. So it's very often where we get some of the most severe storms along frontal boundaries, okay? Then there is straightforward convection, right? So this is intense summer afternoon heating, right? So that's another lifting mechanism. That's a pretty bad photo, I need to swap that out. So summer afternoon heating, convection, important lifting mechanism. We've also got orographic forcing, another mechanism, right? Some of the rainiest places, not some of, the rainiest places in the world are places that are halfway up mountains, where we've got warm, moist air coming off ocean surfaces, like coming off the Indian Ocean into, for example, the Bay of Bengal, or India, or if any of you been to Hawaii, right? Or the West Coast Mountains, the Cascades, the Pacific Northwest, any air that comes in that may be completely stable. If it's forced up a mountain, it can only do one thing. Any air that rises, remember, it cools, gets to its dew point, and you can get thunderstorms developing orographically, right? But they're generally speaking nowhere near as significant in terms of storm development as frontal boundary. So that's just a quick overview of some of the lifting mechanisms. So we've got afternoon heating, convergence, frontal boundaries, and so on. All right. Okay, so that's just some context for you. We tend to group storms into one of two types, one of which we call air mass thunderstorms. And air mass thunderstorms are storms that develop in exactly that, warm, maritime, tropical air masses, right? So this is warm, moist air advected in from the Gulf of Mexico. And so when you look at this diagram here, now this doesn't seem especially hot, but this is a warm, moist air mass coming in here, temperature of 64, dew point of 62, temperature of 78, dew point of 63, right? Any kind of maritime tropical air coming in off the Gulf of Mexico, especially in spring, summer, and early fall. Thunderstorms will develop because you've got that moisture to tap into, right? So we tend to develop, or so we tend to classify storms as those that are developing with a particular type of air mass, and geographically those are pretty widespread. Or we tend to look at storms as being what we call synoptically forced. Okay, so synoptic in meteorology just means a large scale, and this is almost always occurs along the frontal boundary, right? So thunderstorms can develop in a kind of popcorn scattered fashion within a warm air mass, or they can be forced up along a frontal boundary, right? So this is obviously cold front here, and from a Doppler radar, the darker the colors, the more intense the rain. That makes sense, right? Okay. So that's a very broad distinction in thunderstorm terminology, in air mass thunderstorms and synoptically forced storms along the frontal boundary. The frontal ones are much more organized. Okay. So take a look at this. This is a map of the US, obviously, and it shows the number of thunderstorm days in the United States. I don't know if that surprises you or not. I'm going to ask people, so what places get the most thunderstorms? I don't know why they call it the Sunshine State. Because it rains, right? Florida gets the most thunderstorms. Look at that. There's a core hub there, central Florida. It gets over 100 days a year of thunderstorms. Rainfall. something on there. Why is Florida the hub? Everything is bigger and better in Texas. Yeah, that's because yeah. So there's a huge moisture source, right? We've got this peninsula sticking out into the middle of the Gulf of Mexico in the Atlantic Ocean. So you've got the moisture, right? And we also have that moisture. You can see that the yellow there, which is the 50, and then we've got 60. Clearly, if you're interested in thunderstorm climatology, you're probably not going to move to Vermont, right? So you want an area that has that moisture to come in for the start. But when we start looking at tornadic storms and severe storms, once we get beyond climatology and we get beyond the tropical stuff we still have to cover, we'll come back and look at the so-called tornado alley, right? When we think of the most severe thunderstorms, we don't think of Florida, we think of Oklahoma, certainly Alabama, Texas, right? The traditional tornado alley that you've probably heard about, right? Starting there and stretching up to here. So that's where we get the most severe storms, but it's not where we get the most thunderstorms. So I suppose I should really make that distinction here. When we use the term severe, and again, I'm going to come back and do an entire section on this, right? This is the cool, fun stuff. You can only use that term severe thunderstorm if one of three things are happening. Okay? You've either got to have 3/4 of an inch of hail hitting the ground. Okay? If you've got hail, then you've got a severe storm. I was reading a story this morning at 5 a.m. before I went to the trip it's on the BBC. It's called Just How Big Can Hailstones Get? Hailstones get. Quite an interesting story. And again, we're going to look at that when we deal with severe storms later on. So one of three things: 3/4 of an inch hail. You've got to have what we call straight line winds or horizontal winds that are blowing at about 53.5 miles per hour. Okay. Or you've got to have a tornado on the ground. Those are one of three things. You don't have to have all three. You've got to have one of those three things occurring for any thunderstorm to be considered severe. Right? So either 3/4 of an inch hail, straight line winds of 53.5 miles per hour, or a tornado on the ground. Okay. So a lot of those storms in Florida are not severe. They can produce lots of rain. The amount of rainfall doesn't determine whether a storm is severe or not. You can have severe flooding, but that technically is not a severe thunderstorm. Okay. But there's something else going on in Florida. Okay. Florida really doesn't have any more moisture than Brownsville, Texas. But there's something else going on in Florida that causes it to have about 1/3 of the days to have storms. Okay, and here's what it is, right? This is why Florida gets so many storms. It's because a specific type of circulation is set up over Florida, and it's called the sea breeze. Okay. Now, I don't know if any of you are ardent beach people. If you like the beach, I prefer mountains, but you go to the beach, you go out in the morning, you stick up the umbrella and put down the towel, hopefully you put on the sunscreen, you can lie at the beach for a few hours. Very frequently, what happens in the mid-afternoon is you start feeling this breeze coming on shore, right? And that's called a sea breeze. It develops and it gets stronger in the mid to late afternoon. And by the early evenings, it often dies down. And then it reverses and blows offshore. That's called a land breeze, blowing from the land to the ocean, right? So the sea breeze is a unique system and unique circulation that is set up. And it's set up because of the differential heating between land and water. Okay, so we've talked about that a couple of times in the course already, the specific heat of water, right? So if you're sitting on the beach, okay, we know that the sand heats up quickly, right? The land, whether it's beach sand or nearby areas, that will heat up more quickly than the ocean water, right? What that does, okay, the heating over the land sets up a relatively low pressure. Relatively speaking, we're not talking about dropping pressures from 1,000 millibars to 900 millibars, right? It can be quite subtle, but it sets up lower pressure here and a relative higher pressure offshore over the colder water. Okay, that's what the temperature gradient does. Because remember, how does air move? It moves in response to a pressure gradient, right? From high pressure to low pressure. what sets up the pressure gradient? The temperature gradient. Okay, so this temperature gradient that is set up between the warmer land mass and the colder water sets up this pressure gradient. And as that land gets hotter and hotter in the mid-afternoon and the late afternoon, okay, that pressure gradient gets a little steeper and the air begins blowing in on shore as a sea breeze. And that circulation is completed, right? These arrows complete the circulation. If you just imagine this big sort of overturning cell from heating over the land, air rises, moves out offshore, sinks, comes back on land. That's the sea breeze that gets stronger and stronger in the mid-afternoons, okay? At night, right, what happens? At night, the reverse happens, right? The land cools down more quickly and the water retains its heat longer, okay? So the pressure gradient actually reverses and the air begins to move offshore, right? Okay, so how does that work with Florida? Well, what happens with Florida is that it actually has not just a sea breeze developing, but it's got a sea breeze developing on both sides of that Florida peninsula, okay? So here is the land, right? And you've got this air coming in off the sea breeze, you've got heating land and it rises up. You've got that happening on the eastern seaboard of Florida, but you've also got that happening on the Gulf side of Florida. Does that make sense, right? So you may be sitting in Tampa looking out west towards the Gulf of Mexico, and you've got a sea breeze coming on shore because of the land-water differences. Maybe sitting in Fort Lauderdale looking out towards the Bahamas, you've got the same thing going up, right? So you've got a double effect, if you like, in Florida. Not just have you got, as Vince pointed out, you've got lots of moisture there, right? High humidity. And you've got the land heating up, causing the sea breezes, but the sea breezes are actually meeting over that peninsula, right? And so we've got the conditions for thunderstorms. So I'll show you a couple of satellite images here. On the right-hand side, this is an old image, but it works well. It's an infrared satellite that's been artificially colored. This is Kissimmee, I think, Lake Kissimmee in Florida, okay? And here's the eastern seaboard, and these are slightly stronger storms, but you can see the impact of differential heating on this slide beautifully, right? The land heats up more quickly. There's Vince's air mass, right? Lots of moisture, little popcorn, storms all over the place. But the most significant storms occur, or potential for rain, along the front of that sea breeze boundary. So again, let me show you a couple of satellites here. Sorry, I have to keep moving backwards and forward. So we're going to look at a couple. So this is just a sequence, right? This actually is a fire here. That's pointed out here. These are not, right? These are storms. So this is the back edge of the sea breeze front. So this is June 1998. And you've got a sea breeze coming in here. Here's a nice line of storms right there, right? As the sea breeze comes on shore, and here's the sea breeze coming on shore at the back. So let me just flick through these, and you'll see what we're talking about here. So here's 11 June, right? This looks very, very messy. You can see Florida there in the red, that's outlined. So this is 2:15 in the afternoon, okay? So there we go. And then here it is, 16:15, right? Let's look at another one. 18:15. So this one shows it really well here, right? Look at all of this cloud development along Florida here. It's not that there's no clouds offshore because the circulation is still moving around. Okay, that shows it really well. So this is 2015. I should have mentioned that's Greenwich Mean Time. So that's 2:15 in the afternoon, Florida time. Now you can see the back of the sea breeze front. Beautiful, right? There's the line there. And one of the things that you'll notice on this, and you'll see this when we get to talk about severe storms, where you see that cloud development and it looks like someone's eyeing the top of those clouds flat, that's when you know you're in business, right? That's where the uplift in that storm has begun to spread out at the top of the tropopause. But again, we'll look at that in a bit more detail. Right, so this is 8:15 Greenwich Mean Time. Here's 2 hours later, right? So now we're in trouble in terms of weather forecasting here, because here we've not only got the back of the sea breeze front, but here you've got some really large particular thunderstorm tops that we call anvils, and again we'll examine that. Okay, so that's why Florida gets the most thunderstorms, right? This sort of double sea breeze that develops along with lots of moisture. The other classification I just wanted to mention, and then I'll wrap this up, is air mass thunderstorms tend to be what we call single cell thunderstorms, one single convective cell. Okay? So that's another way of looking at storms, either a single cell storms or what we call multi-cell storms. And I'll show you a cross section of a multi-cell storm in a bit, right? So the one thing, so storms have a genesis. This is actually a really important little diagram here. It's from the book, but it illustrates an important point. The thunderstorm has a history, right? It's got a genesis. It doesn't just spontaneously appear as a 30,000-foot storm. So single cell storms have three very distinct stages. Right now, it's an ongoing process, but we can break it down into three key stages in storm development here. Right? One is called the cumulus stage, and that's when whatever the trigger mechanism is, whether it's a frontal system or convergence or tropical convergence or orographic, whatever, the cumulus stage is when you get the vertical growth of the storm, right? Where the storm is dominated by what we call updrafts. And so air is going vertically upwards. And so it's a fledgling storm. We've got low-level warm air coming in. And again, I'm not going to label a particular trigger here, but for the most part, this is a really good example of convection, the cumulus stage of a thunderstorm. The updrafts then begin to develop, right? They grow and they grow stronger. And if all the things are correct, right? In other words, if you go back to your thermodiagram, if you've reached a level of free convection and you can take your hands off the trigger mechanism, then that thunderstorm will grow and develop into the mature phase. And the mature phase of the thunderstorm is where you have updrafts and downdrafts. So you've got air going up, warm, moist air being fed into the storm, okay? And then eventually that air will cool, condense. If the precipitation processes kick in, right? The ice crystal process and the collision and coalescence, and you can get those raindrops to grow and they can fall through the cloud. That's when you get downdrafts and precipitation. Folks, the rainfall, the ice crystals and the raindrops initiate the downdrafts, right? That sucks the cold air down through the storm. So in the mature stage of a thunderstorm, you've got updrafts and downdrafts that are juxtaposed, right next to one another. Okay, and then you've got what we call the dissipating state of the thunderstorm, and that is when the storm begins to die out. That's when the downdrafts dominate the storm system, right? In fact, the downdrafts cut off the updrafts, right? All of that falling rainfall and precipitation itself will begin to cut off the updrafts. It also begins to suck in dry air from outside of the storm system. So it's a fairly simple conceptual model and it works well. Cumulus, mature, updraft, and downdraft. And the dissipating stage is when the storm begins to die out. Here's just a kind of giveaway before we get to the severe stuff later on. In a severe thunderstorm, the mature stage looks different. Okay. And what's key about a severe thunderstorm is that the entire system is tilted over, okay, so that the downdrafts don't cut the updrafts off. In other words, it's like having two escalators like that, where the updrafts are sucking warm air in and the downdrafts out front are bringing the precipitation down, but the downdrafts do not cut the updrafts off, right? That warm, moist, unstable air can continue to be fed into the storm. So that may not make sense. There's a reason why that actually happens. We'll look at that. But that's a key distinction between a regular thunderstorm and a severe storm, is that in a severe storm, that whole system is tilted over. Does that make sense? Any questions on that? Okay, so those are single cell. The reality is that many storms, I think the majority, it's fair to say the majority of storms, are what we call multi-cell clusters. Okay, so instead of thinking of a thunderstorm as taking, I don't know, a big head of broccoli, snapping off one piece, and that broccoli head is the thunderstorm. So that's the cumulus stage, right? In a thunderstorm, most thunderstorms are actually the entire broccoli head, and each of those stalks are a cell at a different stage of development. if that makes sense, right? So the majority of thunderstorms are what we call multi-cell clusters. This image here, this reminds me, you're probably thinking, boy, we're leaving out so much here. Why do we have this big bulging anvil? All of that we'll come back and look at when it comes to severe storms, because that's an indication of severe weather. So right now, just for multi-cell clusters, I like these little cross sections. I think they illustrate this quite well. Again, you may have a storm and it may just look like one gigantic storm like that previous photograph, but actually within that storm are several of these clusters, right? Each at a different stage of development. So cell 4 here would be the developing cumulus stage, right? Cell 3 might be where we have, 3 and 2 might be where we have the mature stage. And then out in front, cell 1 here, which is beginning to die off, where the downdrafts are cutting off the updrafts from the storm, right? And the whole thing begins to feed on itself with warm, moist air being driven in by the back here, and the system will develop. And this may be, you know, I don't know, 15, 20 minutes, half an hour, or something like that. So cell 1 dies out, cell 2 begins to develop and become cell 1, right? And cell 4 now begins to develop, and 5 becomes the small cumulus, the cumulus stage. Boy, I'm struggling today. Okay, so most thunderstorms are these multi-cell clusters that you see. They will roll and die out. This is kind of an interesting one. The reason why these become the cumulus stage is something that's known as the gust front. You've probably experienced this, right? If there's a storm coming into the region, before that rainfall actually hits, the wind picks up and you feel that sort of mini cold front. Those are the downdrafts coming out ahead of the storm, right? And those downdrafts produce this thing called the gust front, and that then acts as another cricket. It's a feedback system, positive feedback system, where the downdrafts push this cold air out, and that forces warm air up along that gust front. So it becomes a kind of self-sustaining mechanism. So that's the rule rather than the exception, right? The thing and I'm going to end early today. The one thing that's important to, I guess, to just re-emphasize here is when we looked at uplift, okay, we were talking about stability. I don't know if you recall this, but I showed you a map that showed regions that had air going up and regions that had air going down. I said the actual vertical motion are very, very gentle, right? Even in a low pressure center. Remember that 0.04 millibars per second? We did a quick calculation and said that generally speaking, it might take, 15, 20, 30 hours for air to just gently go up in a storm system. That's not what we're talking about here, right? That's why understanding stability and getting an air parcel to its level of free convection is so critical, because once you get to that point, then you can have explosive storm development occur within 15, 20 minutes, half an hour, something like that, right? So the speed of uplift is very different in a single cell or a multi-cell storm than it is across an entire region, something like that. And that's why forecasting it is so difficult, right? We just have such a tough time. All we can do is say, well, there's a 50% chance of severe weather. With severe weather, it gets a bit more solid, and you'll see why. Because there's some things going on. All right, questions? Post-spring break model. So here's where we go from here. Okay. We're going to scale out into two areas here. First is tropics. Okay, we're going to talk about tropical meteorology for the next couple of sessions at least, right? So we're going to break this down into two big regions. So tropics, we will deal with the general circulation. So all the fundamentals are out of the way here. Let's deal with the general circulation. We'll talk about things like El Nino, right? We'll talk about hurricanes. Then we'll go into the mid-latitudes. And in the mid-latitudes, we will deal with frontal boundaries and systems, severe weather, tornadic thunderstorms, right? So that'll be all the cool catastrophic stuff out of it. So once we've done tropics and mid-latitudes, then we move on to the last part of the course, and we'll start exploring longer-term things like climate change. So good. Question 2, 1. Apparently. Is it next Tuesday? Sweet. We look at that. Have we covered enough?
Or just looking at what the schedule says, this is tropical weather. 4 2, we're supposed to be.
Can you turn it around? Yeah. All right. What's the deal? Exam 2, 2, 3, okay. What is the exam one? We make up the surface pressure. We've got pressure and number of stability, circulation, thermodynamics, and this. We're just a little behind, right? Interesting. Are we going? Yeah, let me come to that today. I don't want to, we do need to get to the end. We'll probably push that back to, Tuesday, March the 29th. Okay, obviously, if you've got a university excuse, that messes up with the schedule, it shouldn't, but if it does, I'm happy to work with you on that. That's, let me just double check that and spend some time mudding that today. We may need to push it back. Was that the question as well?
No, it was about cloud classification.
Oh, yeah, file classification is going to come back. Yeah, we'll jump into that. All right, cool, then. Thanks, Merritt. What do you think about that?
I don't wait, what's the time? Okay, it's 10 hours.
Yeah, I think that- Monday was great.
Like,